Alright folks, welcome back. Another video tutorial on chemical equilibria. This is the sixth in our little library of videos here, and we're going to talk about the equilibrium constant Kp, which is of course P for pressure. When dealing with gases, of course, it's usually more likely to have a measure of the partial pressure rather than concentration. For equilibria situations, though, this introduces a few extra considerations. Normally when we talk about the equilibrium or the equilibrium constant, we're really dealing with concentration, so moles per litre. If we're talking about pressure, pressure is not the same as moles per litre, is it? It's a different way of expressing how much of something you have, and of course it's related to the volume, and there's all sorts of considerations such as the temperature and so on, and hopefully most of you remember the ideal gas equation. So if we're now talking about pressure, what units are we using for pressure? There's all sorts of different units. You'll hear pressure talked about in pascals, kilopascals. If you're looking at the weather report, it's hectopascals. There's bar, millibar, torr, which is another name for the very old-fashioned torr. Torr equals millimeters mercury, when they used old manometers to measure gases and so on. So we need to be able to convert from concentration to pressure and back and forth and so on. So concentration, something you should be pretty familiar with. The concentration equals the number of moles divided by the volume. Okay, now when we talk about gases, we can invoke the ideal gas equation. So PV equals nRT. So the pressure multiplied by the volume equals the number of moles times R, which is the gas constant, multiplied by the temperature, in Kelvin, of course. And if we were to combine the two, perhaps we could make some sort of interconversion. If I look at expressions number 1 and 2, I notice that they both have N for the number of moles. I notice that they both have V for the volume. Okay, so maybe I can make some sort of expression sort of interrelating these two, and if I sort of mix, first of all I'll rearrange the ideal gas equation, so P equals nRT divided by V. Well, from my first equation I've got N, I can express N in terms of C times V, so I've subbed that into my equation, and I can actually get the two V's to cancel, and I can get pressure equals CRT. Okay, so I've actually got a relationship between pressure and concentration. In fact, RT is really just what's linking concentration and pressure. Well, that seems nice at first glance, doesn't it? But we need to be careful. What are the SI units for volume? Temperature. For R. Well, SI units are very specific. So for pressure, it's pascals. For temperature, Kelvin, not Celsius. For volume, here's an interesting one, meters cubed. That's right, so the SI unit for length is meter. For area, it's meters squared. And so for volume, it's meters cubed. Number of moles, well, we just talk about how many moles we have, and the gas constant in SI units is 8.314 joules per Kelvin per mole. But what about concentration? All the concentrations we've talked about in the past have not been in a number of moles per cubic metre. It's in moles per litre, and that's what we're most familiar with. So we have to be careful if we're going to use this relationship here, because those two V's that we cancelled when we made this relationship, they have to be in the same units. If one volume is expressed in litres and the other is in meters cubed, which is actually 1,000 litres, well, then we've introduced a bit of a bug to our cancellation. So, because by definition we tend to use units for moles per litre, we need to add a factor of 1,000 in our relationship, as there are 1,000 litres in 1 metre cubed. And this is what we come up with. P equals 1,000 times the concentration times RT. So I guess the next question is, if we have a flask with several gases in equilibrium, can we just take the values for the partial pressure and substitute them straight into the Kc expression, or do we need some sort of new expression? Since the pressure equals 1000 CRT, which we saw on the previous page, we rearrange and we can say the concentration equals the pressure divided by 1000 RT. So for the case of 1-to-1 gives 1-to-1 stoichiometry, let's have a look at what the Kc expression would boil down to. Here's the Kc expression, and of course we've got our products on top, and we have our reactants on the bottom of that equation. Now we've got a new expression for the concentration in terms of pressure. So let's sub that in, and we get this huge thing here. So I've got, this is basically the concentration of C, the concentration of D, and A and B in terms of pressure. What's nice is you'll notice we have 2 lots of 1000 RT on top, 2 lots of, I should say, 1 over 1000 RT on top, and 2 lots of 1 over 1000 RT on the bottom. We can cancel those. Fantastic. And what we actually see is that Kc has boiled down to an expression purely in the partial pressures. And this, folks, is the expression for Kp. So I guess what I'm really saying here is that Kc equals Kp. Okay, so what's the point of even having a Kp? We just use Kc, right? What about for the example here, where we have A and B as your reactants, react together, and they give you C plus 2D. So the stoichiometry is different suddenly. So Kp would look like this, yeah? Where, don't forget, we actually have to introduce this exponential term here. So does Kp still simply equal Kc? Well, let's just go through that step again. Kc equals that equilibrium expression there. You notice this is in terms of concentration, not in terms of partial pressure. We sub that into the equation, and suddenly we've got this additional term here. Now I'm looking at this, and suddenly it doesn't look quite so simple. Yeah, I can't cancel my 1000 RT components quite as easily, because if you like, I've got 1, 2, 3 on top, and I've got 1, 2 here. If I try and cancel everything, suddenly it looks a little bit different to how it looked when I had the nice 1-to-1 stoichiometry. And what I do notice is that that does not equal Kp. So in summary, guys, when does Kc simply equal Kp? Well, it's when I have a stoichiometry of 1-to-1 gives 1-to-1. But as soon as that stoichiometry changes, Kc and Kp are different. Okay, so that's really important to remember. So the 2 take-home messages from this video tutorial, guys, is units are important. If your pressure is going to be expressed in pascals, you need to take that into consideration. You need to know what units your volume is being expressed in, and all sorts of things. And sometimes, depending on what's given to you in the question, it might be more appropriate to use Kc, or it might be more appropriate to use Kp. Okay, it's really going to come down to the way that the question and the data has been expressed. The second one is, does Kp just simply equal Kc? Depends on the stoichiometry, so be careful with that one.